The second version of our producer consumer is going to do exactly the same thing, okay, first, but it's going to introduce mutual exclusion, which is going to address the problem I was bringing up in the previous video, which is if we were writing something a little bigger than a single int every time, we might have the producer starting to write some data, let's say 1 gig of data in the shared memory, and halfway through, the consumer will start read the whole thing, which means the half that has been written and the half that is just garbage, random stuff that was in the shared memory segment. So we could observe data corruption much easily if we were writing bigger, if we were exchanging bigger data between the producer and the consumer. Nonetheless, the implementation that we have right now is absolutely not correct. So we are going to pretty much, our first step is going to be to fix this particular flow in version 2. So let's take a look at our code. We have here a copy of producer v1.c and here a copy of consumer v1.c. We have renamed them consumer v2 and producer v2, and we're going to start there to modify these versions and add pretty much a semaphore to help us guarantee mutual exclusion. So who says adding a semaphores says that we need a key variable and an ID variable, just like we did with the shared memory and pretty much every System 5 IPC mechanism. So let's go for it. Key underscore t. Let's call this semaphore semkey mutex mutual exclusion, and we are going to have an int semid mutex. So it's clear that this is a semaphore key and ID, and this is more specifically a semaphore key and ID used to implement the mutex, the so-called mutex semaphore that we have in our instruction. Well, the same way that we were asking for a specific key, let's go ahead and we are going to ask for a specific key for the semaphore. What semkey underscore mutex value should I use? And we are going to read here semkey underscore mutex. I can get rid of one of the get char. Okay. Size of the shared memory segment, that's not going to change. What I need to do, however, is handle the creation of my semaphore array. So I'm going to use the Roshkind library. So create semaphore, and I'm going to put semaphores because we are going to have in version 3 more than one. Semid mutex equal, I'm going to use the Roshkind library we wrote, semcreate with semkey mutex. And that simplify, the detail of dealing with the syntax of the System 5 API. Creating a brand new shared memory segment, well, there is no reason to change any of that, okay? However, before I reach here my producing data loop, I'm going to have to initialize at some point my semaphore. So let's go ahead and do it when we create it. I create my semaphore. What value should it be initialized at? Well, the semaphore mutex is supposed to be taken before I access the shared memory and released after I accessed it. So my usage would be semdown, still using the Roshkind library, semid underscore mutex. I take the mutex semaphore before to access the shared memory, and I release it, semid underscore mutex, and I release it right after. This is a very classic pattern, okay? You access a shared resource that can be corrupt, you take your mutex, mutual exclusion semaphore before, you release it after. But that means that to be able to take it even once, I need to have the semaphore initialized to 1. So initialize semaphores, and I'm going to initialize it the quick and dirty way, which is by doing a semup operation on semid underscore mutex. Okay, I released the semaphore first time when nobody took it. I'm assuming that it was initialized to 0, which is a correct assumption with System 5 IPC semaphores, and I therefore put it to 1, which will allow me to enter here, do a down, then release it to up. And as long as I have this down, since the semaphore was value 1, it's now 0, and anybody else that tried to do a down is going to be blocked, waiting for me to release it here with a up operation. This is pretty much it for the core logic, but I still have a little bit of cleanup to do. When I do my SHM control to destroy the shared memory, I should also do a sem destroy sem id underscore mutex. Okay, I clean up all of my IPC System 5 mechanism. Let me save this. Let's have a look at the consumer now. What's going to happen in the consumer side? Well, pretty much the same thing. Okay, we have here, and I'm going to use a cut and paste. We have here, well, actually I can retype this real quick, need for a key underscore t sem key mutex. We are going to need to not create but open the same semaphore on this side here in the consumer side. Sem id mutex, same thing. All right, then what key should I use? I'm going to cut and paste that because this is exactly the same thing. What key should I use? Well, this is going to be the same thing going on here than with the producer. So let's go back here. We are in the producer. Let's go back to the consumer. There we go. Set the size. Okay, the size is going to be the same. I need to create my to open my semaphore. So I'm going to start with the consumer code again, the producer code again, sorry, right before the size, fixing the size of the shared memory right before here. I'm going to not create, as I was saying, but open my semaphores. So I have a sem underscore open function in my Rochkind library, and I'm going to leave the initialization of the semaphore to be the responsibility of, well, the producer process. There we go. Setting the size of the shared memory will be completely unchanged. Then I'm going to get my shared memory, open it, attach it, so we can scroll down through all of that, get, attach, and then here I go. I am at the point where I want to read from the shared memory. I'm going to do a sem down on sem id mutex to guarantee mutual exclusion, and a sem up on sem id mutex. So same sequence, okay, access the shared resource, do a down, do an up on whatever guarantees you mutual exclusive access. In this case, that's done by a semaphore. The detach is here. I don't really have anything to do on the semaphore, okay, the producer is going to be the one responsible to destroy it. So I'm going to go ahead and go to Conqueror right now, and I'm going to recompile those programs. So I'm going to start by, I need to modify this slightly. I'm going to compile producer v2 into an executable called prod v2, and I have a couple of issues here, and define reference to sem create, sem up, sem down, sem up, sem destroy. I simply forgot to include my Rochkind library, so I'm going to go ahead here. I forgot two things actually. I'm going to do it first. Include Rochkind .h. So I need the include to be able to compile this, and I'm going to save this one, go to the producer, do the same modification, and I need also to compile those executable along with the Rochkind source code. So that means gcc rochkind.c producer v2.c generate producer v2 executable. It's a little better. And we are going to do the same thing for the consumer, so that means gcc rochkind.c cons v2.c generates executable cons v2. Sounds good. Well, let's test it to see how it works. Let's go back to our terminal. In the producer, I'm going to run prod v2, asking me for shared memory key. And here I'm going to run const v2, asking me for shared memory key. So let's go. Shared memory key 123, and I'm going to give the same to the consumer. Messed up, Control C, we start again. 123. The same key mutex I'm going to use for the producer 123. I can use the same number because the ID for mutex are stored separately than the IDs for Semaphore, are stored separately than the IDs for message queue and the IDs for shared memory segment. So you can use the same number. So I'm going to give 123 here to the producers. Producer start real quick. Give 123 to the consumer. You see that both could open their Semaphore shared memory. Let's see what's happening now. Wow, the producer is sleeping very little, so 0, 1, 2, 3, 4, 5, 6, 7, etc. The consumer is lagging, has been sleeping considerably more in some occurrence here. 1, 4, 5, 6, 6, 7, 8, etc. Well, there's not much we're going to observe here because the only thing that happened is that we have the same level of functionality than version 1, but we are guaranteed to not have data corruption, which is a plus, but since it was difficult to observe data corruption, well, it's difficult to observe the benefit on this run. So our next step will be to address the issue of why do we lose, numbers like that? Can't we find a way to synchronize between the two processes? And we're going to use the exact algorithm that is provided to you in the instruction of this exercise. I'm going to press enter here to have the producer destroy everything. A PCS will confirm that all the Semaphore and shared memory segments that existed have been destroyed and cleaned up properly by the producer.